Okay. Okay, so thank you for the remote invitation to talk to you today. I'm really sad that I'm not going to be there in India to share in the joys of the jets at LHC Workshop. But Tuan asked me to talk a little bit about aspects of jets from first principles, and so that's what I'm going to do today in this talk. So I think it's no secret that there's been an explosion of new ideas in QCD over the past almost 10 years. With the development of new jet algorithms like the anti-KT jet algorithm, new calculational techniques for both loop level, multi-leg Feynman diagrams, as well as logarithmic resummation. And the field that I'm particularly excited about is this field of jet substructure. And this talk is going to be about the interplay between this fixed order and resummed explosion of calculations and what we can learn in the context of jet substructure physics. Now, if we just think about jets more generally, when we talk about jets, we're really talking about two different types of things. At one level, we have the idea of a jet as a physical phenomena, the notion that when I have a confining gauge theory, I have a spray of particles that gets collimated due to the collinear singularities of gauge theories. And so that's certainly one meaning of what we talk about when we're talking about jet physics. But there's another meaning of jet, which is a more ambiguous meaning of jet, which is just as an analysis technique, as a method to interpret hadronic final states that the user gets to select. And one of the things that you realize when you think about jets as an analysis technique is that there's no intrinsically right way of defining jets, and there's the freedom to use different analysis strategies to ask different physical questions. And this is shown in this event display here, where you see an example of two different jet algorithms, both of which are infrared and collinear safe. The X-cone jet algorithm, which gives you these blue conical configurations, and the anti-KT algorithm giving you these yellow conical configurations. And you can see that they have a very different reconstruction of the final state. And depending on what physical question you want to ask, one algorithm versus the other might be more appropriate. Now, for this talk, in particular, for talking about jet substructure, the physical question that we want to ask, is how do we distinguish between different underlying mechanisms for jet formation? So if I look at the particles in the standard model, we have a variety of different partons that can give rise to jet configurations. Actually, famously, even leptons can sometimes give rise to jets. For example, a hadronically decaying tau gives rise to a microjet. But if we are doing new physics searches, we want to be able to distinguish between different jet formation. That is, can we tell the difference between jets that are produced by short-distance gluons versus those that are initiated by short-distance up, down, and strange quarks, charm quarks, and bottom quarks? And there are various classification strategies, some more rigorously defined than others, to try to tell these different production mechanisms apart. Of course, famously, you can use displaced vertices in the case of bottom and charm quarks to identify jets that were likely initiated by bottom and charm. Or you can try to use the differing radiation patterns between light quark jets and gluons to try to do some level of quark-gluon discrimination. But the new ingredient that's come to the fore in the field of jet substructure is the realization that when you go into the hyper-boosted regime, that there are other objects that can give rise to jet final states that might be reconstructed as a single jet, namely the heavy resonances of the standard model, the W and Z bosons, the Higgs boson, and the top quark. Some 60 to 70% of the time, those heavy objects are reconstructible as fat jets with 2 or 3-prong substructure. And the field of jet substructure has developed a variety of techniques to try to tell the difference between jets coming from these heavy resonance formation versus jets coming from lighter quark formation. And this has been an enormously successful field, and a successful field that, as I'll try to explain, we can understand certain aspects of it through first principles calculations. So the rise of jet substructure, the rise of techniques to try to do discrimination of different origins for jets, basically determine the parentage of jets. There's two broad categories of techniques that you guys have all been discussing at this workshop. One technique are grooming techniques, which at a cartoon level are trying to improve the invariant mass resolution of these heavy resonances. basically take objects that are intrinsically n-prong-like, remove wide-angle soft contamination that could be coming from initial state radiation, non-perturbative underlying events, or pile-up configurations, and try to remove that contamination to give a nice invariant mass peak. And one technique that I think Sal Rapocho told you about yesterday in his Skype talk was the soft drop declustering technique, which is used as part of WZ tagging at CMS. And here you can see an example of an event of top quarks where the hadronic W was reconstructed to give you a nice peak using the soft drop method. And there's a variety of grooming techniques that are on the market. Another broad category of techniques are discrimination techniques, which are trying to get at the underlying topology of jets, trying to tell the difference between jets that are initiated by quarks or gluons, which are one-prong-like, versus WZs, tops and Higgses, which are two- or three-prong-like, and a huge range of different techniques that are in use. And, for example, CMS in their WZ tagging uses a technique called n-sub-jettiness to try to tell the difference between signal jets shown in these open histogram that are more likely coming from boosted W or Z bosons versus the overwhelming background of jets initiated by quarks or gluons shown in the gray histogram down here. So what I want to do in this talk is to try to talk about discrimination from a first principles perspective. And the way I'm going to do it is by trying to tell you a story. Where I'm going to try to use theoretical calculations to get inside the minds of experimentalists. So here we're going to be talking about W and Z tagging, and in particular the default algorithms that were used for some of the 2016 analyses using boosted W and Z bosons. And we're going to compare the strategy of CMS to the strategy of Atlas with respect to these two strategies, the grooming strategy and the discrimination strategy. So CMS, in its default WZ analyses, has turned to the soft drop algorithm for grooming and this n-sub-jettiness algorithm for discrimination, whereas Atlas uses a technique called jet trimming for its grooming and a discriminant called D2 for its discrimination. And what we'd like to understand is whether these are, in some sense, good choices. That is, can we use first principles calculations to understand whether these are the right strategies or not? And in particular, Atlas and CMS are both trying to optimize performance. So it's a little bit puzzling that they chose different default strategies since the Atlas and CMS detectors aren't so different from each other. So maybe this distinction between these two columns has to just do with details of the detector. Or maybe the different choice of algorithms might just be due to inertia within the collaboration, who coded up which algorithm first. Or maybe there's actually good theoretical reasons why CMS and Atlas are making different choices, and we're going to see something along those lines. We're going to see that what Atlas and CMS are doing makes sense given the way that they perform their analysis. And what the punchline is going to be that the small print here about exactly how CMS uses n-sub-jettiness, in particular the fact that it uses n-sub-jettiness before grooming, and for Atlas, the fact that Atlas uses D2 after grooming, that this can be understood from a theoretical perspective and gives us a little bit of insight into how these algorithms are working. So can we understand these choices from first principles QCD? And once we understand these choices, can we try to use those lessons to construct improved algorithms for maybe the next round of analysis? And in both cases, the answer is going to be yes. And the key realization is that discrimination is different before or after you perform this grooming procedure, and we'll see that from an analytic perspective. And then for the purposes of constructing improved algorithms, we're going to use a technique called power counting to design robust discriminants that in some sense incorporate lessons that both Atlas and CMS have learned in the context of choosing their grooming and discrimination strategies. And with respect to this last point, there's going to be a hybrid. CMS uses n-sub-jettiness and Atlas uses D2. So we're going to develop a hybrid observable that has a little bit of N and a little bit of 2 called N2. And this absolutely insane formula here, which is not the first thing that you would write down when trying to develop a WZ tagging algorithm, this discriminant actually was derived by taking lessons from both Atlas and CMS's experience. And we'll see by looking at 3-point correlation functions within boosted objects, we're going to be able to improve, or at least create a little bit more robust WZ tagging strategies that hopefully both Atlas and CMS will find at least don't perform any worse than the techniques that they're already using. I guess given the remote nature of the talk, it's probably a little bit difficult for any of you to ask questions, but if there's any immediate questions that come to mind, you can try to figure out if you can interrupt me. Otherwise, I will just plow ahead and now dive into this analytic studies of trying to understand these WZ tagging strategies of Atlas and CMS. Okay, so we're going to start with trying to understand the first step, which is the jet grooming step, and see if we can understand Atlas's and CMS's choices, CMS using soft drop and Atlas using trimming. Where do those choices come from? So when we're trying to do a first principles calculation, it's important to remember that there's different layers of jet understanding. That is, if we really want to understand the full structure of QCD, we have to combine knowledge about short distance hard scattering, which produces short-distance quarks and gluons, perturbative gluonic radiation, which creates additional soft and collinear parton emissions from those hard initiating partons. This is usually described in terms of the parton shower. Then non-perturbative physics, for example, in the context of hadronization. And then, ultimately, experimentally, you actually have to reconstruct the hadrons you see. But actually, at the LHC, with the fantastic reconstruction performance of both Atlas and CMS, the mapping between the hadrons that we get and the particle flow reconstructed objects in the case of CMS or the topo clusters in the case of Atlas, there's actually a fairly good match. And so the observables that we see at the detector level are quite close to what we see at the hadronic level. And that motivates first principles theory calculations where we study the fundamental energy flow without any attempt at doing detector smearing, the fundamental energy flow, and try to predict what those radiation patterns are from first principles. And there's been an enormous growth in these theoretical calculations trying to understand a variety of aspects of jet formation. So here's my attempt at a semi-complete bibliography of first principles calculations that I'm aware of that have been performed to date, ranging from trying to understand the one-prong structure of jets, the two-prong substructure of jets, the three-prong substructure of jets, even certain non-perturbative infrared and collinear safe aspects of jet formation. And what's exciting about this list is that they use a combination of different techniques in QCD, ranging from fixed order calculations to direct resummation to soft collinear effective theory. These non-perturbative techniques are often described using renormalization group evolution. And there's also new calculational techniques which have pushed a little bit on the boundaries of QCD. Techniques, for example, like Sudakov safety and multi-differential projections, which have enabled calculations that might otherwise seem hopeless or ill-defined, actually get a nice definition in the context of resummed perturbation theory. And just as a benchmark for how far the field has progressed, just last year there was a milestone reached by a group at Harvard with the first next to leading log plus order alpha s squared calculation for substructure and PP collision, where the soft drop mass distribution was actually calculated with realistic error bars, and that was really a triumph calculation and one that set a high bar for future investigations. Now, for this talk, I'm not going to be really talking about precision first principles calculations. I'm going to be more talking about qualitative aspects of first principles calculations. And for me, one of the most surprising examples of a first principles calculation that just completely blew me away when I saw it for the first time was a calculation of this trimming procedure. If you recall, this is Atlas's default technique in the context of WZ tagging. And trimming seems at first glance to be an algorithm that would be very difficult to predict from first principles because it involves taking a jet, partitioning it into subjets of a subjet radius size of r sub, throwing out subjets whose energy fraction is less than a certain cut value z cut, and then after performing that thresholding, you get this final trim jet. And this seems like a very algorithmic procedure, and one for which you'd be surprised if you were able to do an analytic calculation, especially given that there's these two parameters in this algorithm. And indeed, if you look at just a simulated invariant mass spectrum for trim jet mass, just let's say for QCD background events here for 3 TeV quark jets, you find a distribution that does not seem amenable to first principles calculations. You see a rise, a kink, a plateau, another kink, a hump, and a drop-off. And you'd be a little bit surprised if you saw a first principles calculation have all those interesting features. But in this inspiring paper by Dasgupta, Fregoso, Marzani, and Salam from 2013, they did a first principles resummed calculation of trim jet mass, and they found exactly that. A rise, a kink, a plateau, a kink, a bump, and a drop-off. And they were able to analytically understand this structure. The hump here is actually the classic Sudakov form factor that appears in a variety of first principles calculations with resum mass distributions. There is these kinks actually come from these two parameters in the algorithm. One kink is associated with the subjet radius, and the other kink is associated with the z-cut scale. And that plateau corresponds to single logarithmic behavior that can again be understood analytically. And what you can see is that you can see that, at least if you're in this plateau region, that you have a really smooth background distribution. And so this is the mass distribution for background jets. But if your signal happens to be lying in this kinked region, then you can do nice sidebanding around that invariant mass and do nice signal background separation using trim jet mass. So from this first principles perspective, actually trimming seems like a reasonable strategy, apart from a little bit of the confusion about what happens if your signal straddles the plateau and peak regions. So at least Atlas's strategy looks like it's reasonably well behaved. What about CMS's strategy of soft drop declustering? So this is a strategy that takes a jet and organizes the constituents of the jet into an angular ordered clustering tree. This is known as a Cambridge-Auckland clustering tree, and to my knowledge, the first use of this type of tree in a grooming context was by Butterworth, Davison, Rubin, and Salam in the context of the mass drop declustering strategy. But in any case, you take this clustering tree, which is a reorganization of the jet constituents organized by angle. And if you want to remove contamination, then you want to remove wide-angle soft radiation. So what you do is you take this clustering tree and you just lop off radiation to groom the clustering tree, where the decision about where to lop off the radiation depends on two scales. It depends on the momentum fraction carried by the two prongs of at each 1 to 2 stage in the clustering, as well as the opening angle between those two stages of the clustering. And what soft drop declustering does is it says remove wide-angle branches from the tree until the momentum fraction is balanced. That is, the momentum fraction is larger than the z-cut value times the theta g to an angular exponent beta power. So soft drop declustering has these two parameters, z-cut and beta. Z-cut is an energy threshold that's similar to the trimming energy threshold. And beta is an exponent that can be used to adjust how aggressive the groomer is, where beta going to infinity corresponds to less grooming. Beta goes to minus infinity corresponds to more grooming, with beta equals 0 corresponding roughly to the original BDRS mass drop procedure. And you can now imagine doing a first principles calculation of the soft dropped mass distribution as you adjust to this parameter beta. So using the same techniques that were done in this previous trimming calculation, you can repeat those types of first principles calculations in the case of the soft drop groomed mass, where again, you're taking a jet, you're throwing away soft radiation, and you want to figure out what the groomed jet mass distribution is. And you can see as that you go from the black to the blue to the red to the green to the magenta, you see the peak go from a large Sudakov peak in black to a smaller Sudakov peak in blue, red, green, and magenta as you dial down the beta parameter. And you might say, geez, what's the chance that this structure, where you again see a rise, a kink, a hump, a fall off, could that really be predicted from first principles? And indeed, using the same resummation technique, you can understand these peak structure is again coming from pseudocall form factors. The kink location is coming from z cut, and the parameters beta is controlling exactly how high the pseudocall peak is, with the special value of beta equals 0 corresponding to the removal of double logarithms and the flattening of the mass spectrum. And indeed, CMS has adopted beta equals 0 as its default strategy for boosted W and Z tagging. And that makes sense, again, for this reason of sidebanding, that if your peak is somewhere on this plateau, you have a nice smooth mass structure on either side of that peak. So if I just look again at the mass spectra that Atlas and CMS have achieved using these discrimination strategies here from CMS with a sample of boosted tops where I isolate the W peak, and here in an Atlas analysis separating out W plus jets from a multi-jet background, you see a nice isolation of mass peak at around 80 GeV in both techniques. And this can, again, be understood because both grooming strategies could give good signal isolation. They push the background down to small values of the mass, leaving a nice plateau region where you can look for a signal bump. So in our theoretical investigation of these first principles, using first principles to understand Atlas and CMS's strategies, both Atlas and CMS, their use of these algorithms makes perfect sense. So I give them both checks with a little bit of an asterisk on trimming. Both soft drop and trimming have primary kinks at a location of mass that's correlated with the z-cut value, whereas Atlas has a secondary kink at a slightly smaller scale. And as one goes to higher and higher boosts, where the signal might be pushed into this region below the hump, you might have to worry a little bit about the secondary kink. But again, in a region that's being currently used, both strategies are equally good. And maybe I should just make a plug, since I know Steve Ellis is in the audience there, that the pruning algorithm, which for some reason, which I don't fully understand, CMS has transitioned away to from its default strategy. Actually, pruning also has similar behavior to both of these, that you have the same kink structure and secondary kink structure. And from an analytic perspective, pruning is a perfectly sound strategy for grooming. And in some sense, splits the difference between soft drop and trimming in terms of what the analytic structure of the background is. And so I would implore both Atlas and CMS to keep pruning as part of their toolbox going forward, not just to keep Steve happy, but because also it has perfectly well-defined theoretical behavior and performs admirably as a groomer. Okay. Was that Steve opining in the background? Okay, so now I'm going to turn to discrimination strategies from first principles. And here things get a little bit more complicated because what Atlas and CMS are doing in terms of their discrimination, that is telling the difference between one-prong versus n-prong jets, at first glance they look quite different. And it might be surprising that you could do a theoretical analysis at all to determine which strategy is better than the other. So the strategy that CMS is using for their WZ analysis is this observable n subjettiness, which is discrimination based on subjet axes. So for this part of the talk, I'm going to be using dimensionless kinematic variables, where the transverse momentum of particles in the jet I'll be describing by z, and the opening angle, just for simplicity, instead of using delta r's, I'll just be using the opening angle theta here. And what n subjettiness is doing for boosted WZs is looking at the ratio of tau2 over tau1, which when written in terms of this dimensionless kinematics is the sum of the constituents of the jet, the momentum fraction carried by each constituent, and then the minimal distance to candidate subjet axes. So here you can see I have two axes given by green with little x's here. And someone has to actually give me a definition of what I mean by subjet axes. But once someone gives me a definition of that, I sum over all particles, and I take that particle, here shown as an orange particle, and I calculate both the distance to axis 1 and the distance to axis 2. I take the minimum distance, and then I sum over all particles. That's the numerator of this n subjettiness ratio, and the denominator is the same thing, only with respect to one central axis. And there are a variety of different techniques to try to determine that subjet axes, but one is by actually finding the axes that minimize the numerator and denominator separately. The details don't really matter very much. What I want you to appreciate, though, is that this is a axis-based discrimination strategy where small values of n subjettiness correspond to the case for all the radiation is aligned along these two subjet axes. So if I had an idealized decay of a W or a Z boson with, let's say, just a single particle corresponding to each part of the hadronic W decay, then I'd get ideally 0 in the numerator because those two particles would just line up with one axis and the other axis in the numerator. And this is the strategy that CMS uses, and it's a successful strategy for WZ tagging. Now, Atlas does something that at first glance seems rather complicated. They do discrimination without any axes, and they do it in the context of these objects called energy correlation functions. And this is an axes-free probe for jet substructure, and I must admit, it is not immediately obvious how this observable works because it looks rather complicated. So this D2 observable that Atlas uses is based on the ratio of energy correlation functions, 3-point correlator, known as E sub 3, divided by a 2-point correlator, known as E sub 2, raised to the cubed power. So that is a interesting combination of observables. Again, not obvious why it should work at all. The numerator here is a 3-point correlation where I take three of each triplet of particles, I, J, and K. I multiply their momentum fractions together, and then I take all three possible pairwise angles, theta ij, theta jk, and theta ki, take that whole thing, raise it to the beta power, and then in the denominator, I take instead pairs of particles, zi and zj, as well as their pairwise angle theta ij raised to the beta power, and then I take that whole denominator and I cube it. So how is this possible that this is a good WZ tagger? Well, one thing that you can immediately maybe intuit is why there's a 3 here in the denominator. Why is it that we cube the denominator? Well, when we do jet substructure, we are imagining that we have boosted objects that have a range of kinematics. And so we want to make sure that we are sensitive to a high range of kinematics and that our discrimination strategies don't fundamentally change as I go into the hyper-boosted regime versus the moderate-boosted regime. These momentum fractions, Zi, these are objects that are basically invariant to boosts, at least boost along the jet axis direction, whereas opening angles scale inversely with the degree of Lorentz boost. So if I have a numerator that scales like 3 powers of the angle to the beta power, to have something that will roughly scale invariantly with Lorentz boost, I want to take theta to the beta, and to match the 3 powers of theta in the numerator, I want to now raise that to the cube power. So the way to understand why it's cubed here is to have a quasi-Lorentz invariant discriminant that will work over a wide range of kinematics. Now, why are we taking this particular combination of correlations? Well, this turns out to be a good that when I have a jet that's composed of just 2 prongs, well, in the idealized limit where I just have a jet composed of just 2 particles, I can't even define the 3-point correlation, so the numerator is effectively 0. And so just like the n subjettiness ratio tau2 over tau1 went to 0 for a 2-prong configuration, this D2 observable also goes to 0 effectively in a 2-prong configuration. And so that's the reason why D2 is a good discrimination strategy. And in fact, if I just look at the distributions that Atlas and CMS see for their n subjettiness and D2 energy correlation function distributions, actually both of these observables give nice single signal background separation. I showed already the n subjettiness distribution where the open histogram is signal and the filled histogram is background. You can see with the Atlas distribution where the blue distribution is signal and the red is background. There's a nice separation in both cases. And what we'd like to understand is, well, can we understand this behavior from first principles? Can we understand why both of these appear to be good discrimination strategies? And then also try to understand why Atlas and CMS ultimately decided to make different choices for which their default would be. So n subjettiness turns out to be the easier one to understand. So let's start with that first. So with n sub jettiness, we're trying to compare the parametric behavior of the denominator tau1, the numerator tau2, how it behaves on the background of quark and gluon jets versus the signal of boosted WZs. And what you can see is that to the degree that n sub jettiness is just saying how n sub jetty is a jet, for a quark or gluon background jet that doesn't really have any intrinsic substructure, whether I try to measure substructure with one jet or I try to measure substructure with two jets, basically the degree of overlap is essentially the same. And at least parametrically, tau1 and tau2 are essentially identical. So for a quark and gluon background configuration, at least parametrically, you expect the ratio of tau2 to tau1 to basically be parametrically just 1. That is, one-prong jets don't show any particular preference for being one sub jetty versus two sub jetty, so the ratio just is an order 1 number. By contrast, for a WZ signal event where I really have visually by eye two well-separated prongs of energy, tau2 is much smaller than tau1 because the radiation is much better confined to the two subjets as defined by tau2 compared to tau1 where the axis has to try to split the difference between the radiation. And so the WZ signal has tau2 parametrically less than tau1. And so the signal actually occupies a parametrically distinct region of phase space. And that's the reason why the tau2 over tau1 ratio is a good discriminant for two-prong substructure. And indeed, that's what CMS uses as its default. Now, you can ask the question, what happens if I apply grooming to my jet? Because that's going to be part of the story in a couple of slides when I go to the Atlas case. And when you apply grooming to the jet, with n sub jettiness, basically nothing changes. So I'm going to flip from this slide to the next slide. And if you aren't paying attention, you might not even be able to notice that anything's changed. But I've actually, with grooming, removed some of the soft peripheral radiation from the jets. And you can see just by eye, the degree of overlap between jets didn't really change when I got rid of the soft peripheral radiation. That is, the soft radiation was already providing essentially a subdominant contribution to the distinction between tau2 and tau1. And so we have a parametric separation between one and two-prong jets, even after we remove soft peripheral radiation. The power counting is what we would say is basically the same between one-prong and two-prong configurations with or without the presence of the soft radiation. And so this means that n sub jettiness, when used with or without grooming, in both cases, you expect a good performance. So coming back to the scorecard, where CMS is using n sub jettiness, in their default analysis, they actually use n sub jettiness before grooming. But this first principles analysis has said that basically the same strategy would also work after grooming. But in CMS's performance studies, they find somewhat better performance just numerically when grooming is not applied versus when grooming is applied. And so they do the correct thing, which is when you have two different options, but one performs better, you use the one that performs better. And that's CMS's strategy, which again seems theoretically sound. Now with Atlas, we're going to do the same analysis in just a second, and we're going to see an interesting asterisk here, where we're going to see that D2 is a good discriminant, but that there's another condition that we want to apply to substructure discriminants, not just that they're good at discrimination, but they're stable to changes in the experimental analysis. And that little bit of subtlety is going to explain why the analysis of Atlas and D2 is a little bit more complicated than the n sub jettiness case. And so that's what I'm going to be turning to next. Okay, so to go to this more complicated case of D2, I need to introduce another theoretical concept, and that's the concept of power counting. And so I alluded to power counting already a little bit, but essentially power counting is the way of incorporating theoretical knowledge while doing essentially the bare minimum of a theoretical calculation. And it's a very convenient way of organizing one's thinking about jet physics without actually having to dive into the real analytics of a jet calculation, but still understand, at least parametrically, how different observables behave. In particular, we're going to see the power counting logic as applied to D2 is going to give us some surprising and useful insights. So where does power counting come from? Well, power counting comes from QCD itself. And one of the textbook things you learn about QCD is that there is factorization of scattering amplitudes in the collinear limit. That is, if someone asks you to calculate the scattering cross-section for 2 to n process, well, that in general involves a whole set of Feynman diagrams, of course, that you could extend to all orders in perturbation theory. But in the special limit where 2 of those partons become close, the cross-section factorizes into the production cross-section for a 2 to n-1 body final state with a straight product with the splitting functions. So at this lowest order, it's a 1 to 2 splitting function. And this is an extremely useful fact to know about QCD, or really any gauge theory, that complicated scattering amplitudes, when partons become collinear, have this simplified factorized form, where you can separate out the wide-angle parton production kinematics from the collinear production kinematics, and in particular factorize out the splitting functions, which depend on the opening angle theta and the momentum fraction z versus 1 minus z between the 2 partons. And for the purposes of this talk, I'm only going to be working at basically absolute bare lowest order, where at this bare lowest order, the only thing that can happen as far as a splitting function is concerned is that a hard quark or gluon can emit soft gluons. And the propensity to emit soft gluons is proportional to the Casimir factor, which for quarks is 4/3 and for gluons is 3. And the splitting function can be converted into a splitting probability. And the splitting probability for a quark or a gluon to emit a soft gluon is related to 2 times alpha s over pi, that color factor I just mentioned, multiplied by 2 singularities. The collinear singularity of QCD, which is where this collinear factorization was derived, and the soft singularity of QCD. And this splitting function explains, at least at a heuristic level, a lot of the features of jet formation. Because of the collinear singularity of QCD, missions want to be collimated in the direction of an existing hard parton. So that's kind of one of the ways of understanding why jets form. And then the soft singularity tells you that there's typically a hierarchy between jet emissions. Now, this textbook QCD about the splitting function can be actually used as a calculational technique. And famously, if you iterate this splitting procedure 1 to 2, 1 to 2, 1 to 2, ad infinitum, then that's actually how you can build up a parton shower Monte Carlo generator. But for the purposes of what I want to talk about right now, we just want to use these soft and collinear singularities for power counting. And what we want to say is, well, because there's a propensity for emissions to be soft and a propensity for emissions to be collinear, we want to categorize the emissions within a jet by the degree of collinearity and the degree of softness. And that's this technique called power counting. So we acknowledge that jets are more complicated than just their parametric scaling, but we can use the parametric and the parametric scaling of observables. That is, use the parametric scaling of partons to predict the parametric scaling of observables like D2. So what does this look like? Okay, so if I look at a quark or a gluon, we have 2 types of modes that we have to consider when trying to assemble a jet, at least in this extreme soft or collinear limit. So one are collinear modes and one are soft modes. And from a power counting perspective, collinear modes are modes that carry an order 1 fraction of the energy of the jet. And soft modes are ones that power counting are capturing soft singularity of QCD and carry a small soft fraction z sub s of the momentum within a jet. And then in terms of angles, collinear radiation wants to be at small angles. That's the d theta over theta structure of the splitting function. Whereas soft radiation would have generically order 1 angles, or angles that are basically the same size as the jet radius. Okay, so this is the power counting for quark or gluon backgrounds. Now, if we instead have a boosted W or Z, well, the power counting is different because a boosted W or Z actually is composed not just of soft and collinear radiation, but actually composed of 2 collinear prongs of radiation, one for each of the quark and anti-quark quark direct. So around the W to QQ bar decay, we'd have collinear radiation around one prong and collinear radiation around the other prong. We also have dipole radiation between the quark and the antiquark, which are given the name of collinear soft, as well as more generic soft radiation that might be present in a more complicated event, for example, coming from initial state radiation, which again is at kind of at large angles with respect to the collinear directions. And so for this two-prong signal, we have energies that are order 1. We have these collinear soft modes, which have kind of an intermediate energy of Z sub Cs, these soft modes, which have the softest energy of Z sub S. And then the angles between the modes, collinear modes have this small angle, power counting-wise, theta Cc. Radiation between the two prongs has an angle given by the angle between the two prongs. And again, soft radiation is going in all directions. So these modes can be used as the first step in formulating a rigorous factorization theorem for trying to calculate from first principles. But we can actually just use these power counting modes to estimate how discriminants scale. So let's D2. D2 is taking all triplets of particles, taking their 3 pairwise angles, and dividing that by all doublets of particles via their single pairwise angle raised to the cube power. And just for simplicity in equations, I want to set beta equals 1 so I don't have to carry around factors of beta in this power counting analysis. So what power counting says, okay, you want to look at all triplets of particles? Fine, do it, but do it for these power counted modes. Look at collinear, collinear, collinear combinations, collinear, collinear soft combinations, collinear soft, soft, and not shown here are soft, soft, soft modes, which are actually subdominant in this analysis. And then you can do the same thing in the denominator, take all pairs, either collinear, collinear, collinear soft, or soft, soft. Again, the soft, soft mode is subdominant. And then we can just use the fact that this Z and theta in D2, well, that maps exactly on to the energies and angles that we had before in the power counting. And so we can estimate parametrically what the size of this D2 observable is in parametric scaling of these collinear and soft modes. Now, if you look at this formula, I don't know, I've stared at this long enough that I can read it, but if you haven't seen this before, we basically have 3 different terms in the numerator, 2 different terms cubed in the denominator. It doesn't seem like this simplifies in any particular way. But imagine what would happen if you had a jet that was dominated by soft contributions. Well, if you had a jet that was dominated by soft contributions, then I'd have Zs squared in the numerator, but Zs cubed in the denominator. And that means that if soft modes dominate, this D2 observable would scale like 1 over Zs. And remember, Zs is a small number. And if you map that onto the kinematics of the jet, roughly speaking, 1 over Zs is like the PT of the jet over the mass of that jet. And so if you apply this D2 distribution to ordinary quark and gluon backgrounds, you can see this D2 distribution is extremely sensitive to the PT in mass that you choose. And so this can be shown here for jets that have a fixed PT, but I slide the mass window around. You can first see that this D2 value is gigantic, extending all the way out to 80, 100, 120. So this is a huge value of the observable because I'm sensitive to the softest scales in the jet via this 1 over Zs value. And you can see that if I was trying to look at, let's say, a W mass peak, if I looked below the peak, can I select it? There you go. Below the peak, 60 to 80 versus above the peak of 80, can't select it, 80 to 100, that the distribution slides wildly around. And so if that were really the case, you'd have an observable that might be really good at signal background separation, but it would be highly sensitive to the choice of cut that you used. And if you're highly sensitive to the choice of cut, this is not a good experimental strategy. And in this sense, it is really surprising that Atlas decided to adopt this D2 observable because it's one that really is not amenable to sideband analysis. But there's an asterisk, if you remember before. Atlas does not apply D2 generically to jets without any other procedure. Atlas applies D2 to jets only after it provides this grooming procedure, in particular after it performs the trimming procedure. And what does grooming do? Well, grooming parametrically removes soft wide-angle radiation. So what does it do? It takes away all the soft modes and leaves me with just collinear modes. And if I recalculate this D2 distribution using only collinear modes, well, what do I find? Well, triple collinears give me theta cubed in the numerator. Pairs of collinears give me theta in the denominator, which gets cubed. And parametrically, I just get one. That is to say, no matter what the jet PT or the jet mass is, ordinary quark and gluon jets just have a parametrically stable background distribution. And so after grooming, D2 is parametrically stable. No matter whether I put a cut at below or above the W mass window, I get a beautifully stable distribution. And this is what Atlas does in its analysis. And it's, in some sense, the only reason why they can use D2 at all. In general, D2 is an unstable distribution, unstable to mass and PT cuts. But after grooming, it becomes parametrically stable. Of course, having something that's parametrically stable, that's not good if it doesn't actually discriminate against the background. But we can perform the power counting analysis on the background configurations. And just for interest of time, I'm not going to go through this in any detail. But you can show that D2 is parametrically much, much less than 1 for jets that have 2 prongs with just dipole radiation in between. So the signal is parametrically distinct from the background. This explains why Atlas finds good discrimination performance with D2. But again, only after grooming. And so this asterisk here is to say that Atlas's strategy makes perfect sense after grooming, but would not have made sense before grooming. And Atlas's final default WZ tagger, which is given the name of R2D2, which has nothing to do with Star Wars and everything to do with the fact that trimming is used with a radius parameter of 0.2, and D2 is used as the discriminant. You can see here on this ROC curve that the signal efficiency for a given background rejection is better for D2 compared to other observables like N sub jettiness. And so Atlas has adopted this R2D2 strategy. And this is a theoretically sound thing to do. It would not have been theoretically sound if Atlas didn't groom, but because they do groom, this is a theoretically sound strategy. And in fact, both Atlas and CMS are doing things that are theoretically sound, applying grooming procedures, which is good, and providing discriminants, which are parametrically stable, with N sub jettiness parametrically stable both before and after grooming, with Atlas parametrically stable only after this grooming. And again, we can understand this parametric stability by using first principles QCD. Okay, so at this point, having understood the mind of Atlas and CMS from a first principles perspective, now we want to see if we can go a little bit deeper and try to use this lesson in order to construct new observables from first principles. And so looking at the time, I guess I started 10 minutes late, so I'll just go on for another 10 minutes just to talk a little bit about this new angle on jet substructure, and then we can maybe do a couple of questions. Yes, Tune.
You have infinite amount of time. Just go on as
I have what? I have infinite amount of time, you said? Okay, I will continue on to the extent that the audience is interested. Okay, so let's talk about a new angle on jet substructure and return to this thing that I advertised at the beginning, which is that we could hybridize N sub jettiness and D2 to come up with this N2 observable. And where the heck did this object come from? Well, this object came from power counting, and that's what I want to explain to you now. So these energy correlation functions, if we want to have observables that are parametrically distinct, what we want to do from a power counting perspective is that we want to have different numbers of energies and angles in my observable. And so the ordinary energy correlations were summing over n tuples of n energies and all pairwise angles. But if I want to explore more generally the angular structure inside of jets, well, let's take the n energies and multiply by the v smallest angles among that n tuple. Now, why is it the v smallest angles? It turns out that if I use the v smallest angles among that n tuple, that this choice is infrared and collinear safe. And with a little bit of thinking, you can convince yourself that basically any observable in the power counting regime, you can Taylor expand it so that effectively you're always looking at just the smallest angles. And this gives rise to a new type of energy correlator, which has, let's say, an embarrassing number of superscripts and subscripts. So the ordinary energy correlator is E with an N subscript. And now because I've added this V smallest angles, I have to put a subscript on the other side. And then I have a choice of the angular exponent here, beta, which I'm now putting as a superscript in parentheses. So this is an observable that only someone who likes hypergeometric functions could love. But it is an interesting way of systematically dissecting the energetics and angular scales inside of a jet. And you can imagine, basically calculating this energy correlation for 2, 3, 4-point correlators for the number of angles ranging from 1 all the way up to the number of total n choose 2 pairwise angles within a jet. You can imagine trying to look at different physics in the collinear versus soft regime by twiddling this angular exponent beta. You have a lot of different things that you could try to study with this, and a huge range of observables that you could try to construct out of this general category of energy correlators. And this general category was something that I recently worked on with Ian Molt and Lena Nessib, and we had a lot of fun parametrically understanding the types of behavior that you can get when you look at different energy and angular scalings. Now, for the purpose of this talk, we're going to be interested in generalizing this D2, or at least looking at an alternative to this D2. And that's based on 3-point correlation functions. And so the standard 3-point correlator with 3 angles in this embarrassing notation is now 3E3. So 3 angles, 3 energies, and that's the numerator used in this D2 observable. But I could also look at 2 angles and 3 energies, or 1 angle and 3 energies. And these are all different ways of dissecting the jet that scale differently with angle. So in pictures here, if I want to probe hierarchical jet substructure, but with different angular scaling, the 1E3 looks at all 3 angles, but only takes the smallest one. 2E3 looks at all 3 angles, but only takes the 2 smallest ones. And 3E3 is the standard one that looks at all 3. And from these, you can imagine trying to now build new substructure discriminants. And so that's what we did. We constructed new boosted WZ discriminants based on these. And they have funny names. So the 1-angle one is called M2. The 2-angle one is called N2. And then the 3-angle one was called D2, but we explored the possibility of actually using different behavior in the numerator and the denominator for this beta exponent, exploring different angular scaling in the numerator and the denominator. And one combination which is kind of interesting is D2 with a superscript 1, 2. If during Q&A, I can explain to you why that's an interesting combination to look at. But one way of understanding where these came from is that we took these 3 different possibilities for the number of angles, 1, 2, or 3, and then divided by the pairwise 2-point correlator raised to the appropriate power such that you got boost invariance along the jet axis. And just to remind you, energy fractions stay more or less invariant under boost along the jet axis, but opening angles scale inversely with the Lorentz boost. And these particular M2, N2, and D2 combinations are the ones that have the same angular scaling in the numerator and the denominator, so they're expected to work over a wide kinematic range. And for anyone who's interested in boosted top quarks, we also constructed a observable called N3, which is similar to this N2, but has 4-point correlators involved as relevant for boosted top quarks. But again, we could talk about that offline if you want. So if we look at these discriminants, let's try to understand why, among these discriminants, why N2 as a discriminant is special. Why is it that N2 is the observable that I'm highlighting as being particularly interesting in terms of finding a hybrid between ATLAS and CMS. So we'll go back to our parametric background study, and now we're going to do this parametric background study for this N2. And now N2, again, has this crazy functional form. It has products of 3 energies in the numerators, products of 2 angles in the numerator, where I take the minimum over all 2 pairwise sets. The denominator is 2 energies with 1 angle, and I square it to give me an approximate Lorentz boost along the jet axis direction. And if I then do this trick of taking all triplets, either collinear, collinear, collinear triplets, collinear, collinear, soft, soft, as well as soft, 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 which is subdominant, do the same thing at the denominator. And if you stare at this long enough, you will realize, wait a second, the numerator parametrically is really parametrically identical to the denominator. That is, if I just square out the denominator and ignore factors of 2 in the cross term, the numerator and the denominator are parametrically the same size. And so actually this N2 observable is parametrically stable in both the soft and the collinear regimes. And so whether or not I do grooming or don't do grooming, this N2 observable has the same parametric behavior. This is exactly what we saw already with the N sub jettiness observable, where grooming versus not grooming didn't change the parametric behavior. And now we're going to see this with this N2 observable. So N2 before grooming, derived using this power counting to get nice signal background separation in terms of performance, where for boosted Z's we see a nice separation between the Z's shown in red and then the dash curves for quark and gluons. Nice separation shown here for signal background performance. But also we see this relative robustness to the choice of mass cut. Whereas I make different mass cuts, the background distribution doesn't change much. And in fact, the one distribution for which the background does change, this high mass spin here, actually the reason why that's changing is just because for this particular PT range and this particular jet radius, actually this mass window is borderline in the regime where the whole jet can fit inside of a cone of radius 1.0. So actually here, if I went to a little bit larger boost, then these would all be lining up exactly on top of each other. So we see good performance and good robustness before grooming, as well as good performance and robustness after grooming. Now, numerically, the distributions change. So even though parametrically grooming versus not grooming are parametrically the same, numerically they are different because I have actually removed radiation from the jet. But it's still in terms of performance, I get nice separation between Z's, light quarks, and gluons. And again, the same robustness to the change in mass and PT cut. And both of these behaviors could be understood from a power counting perspective. And just flipping back and forth between these slides, the power counting technique is very good at predicting parametric behavior. But again, numerically, it's not the same. So before grooming versus after grooming, before grooming versus after grooming, the distributions are changing. And in interesting ways, before grooming, quarks and gluons actually look the same, whereas after grooming, quarks and gluons look different, which is fascinating. But that's behavior that can't be predicted just from power counting alone. But the power counting can tell you which observables at least have this nice stability property, which is one of the things that you'd like to have in an experimental analysis. And if I just carry forward this analysis to rock curves, whether I do things before grooming or after grooming, and whether I'm trying to discriminate Z versus quark versus Z versus gluon, this new observable, this N2, does either the same or a little bit better than previous observables. And what you can see in this plot is actually something really fascinating. Look at my 3 new observables, M2, N2, and D212. You can see that these 3 observables, before grooming, are all over the place. M2 barely does better than guessing. N2 does really well, and D2 is somewhere in the middle. Okay, so these observables have totally different behavior before grooming, yet after grooming, their performance is nearly identical. And you could say, how is that possible? Well, from a power counting perspective, these soft modes change the scaling of the numerator and the denominator of this M2, N2, and D12. And before grooming, the scaling is all over the map, such that they have very different discrimination power. After grooming, they're parametrically identical observables, which is why we defined all three of them. And again, these behaviors are one for which the power counting analysis gives us nice insights into what's going on. Okay, so this is what I wanted to tell you about this N2 observable. Yes.
Hi, this is Vikram. I have a question for you.
Yeah. Yes.
So it seems that after grooming, your discrimination power gets worse for Z versus loop.
Yes.
So do you recommend not grooming the jet then?
No. There's this. This is a battle that I had with my co-authors, and I lost the battle. And every single time I've given a talk like that, not like this, someone smart like you points out the same thing I was trying to convince my collaborators of. So here, the Rock curves are normalized to a fixed mass window. So notice that all the Rock curves go to 1, 1 in the corner here. And that's because we basically taken out the mass window cut. And actually, if you look at the rejection factor just by mass alone, groomed mass gives a factor of 3 to 5 better background rejection just by itself. So these distributions don't tell the whole story. This is the performance after grooming. It is indeed true that after you perform grooming, the relative importance of discrimination is less. But the absolute performance between these two things is actually quite similar. And so at the end of the day, whether you do before grooming or after grooming, you get comparable performance. In fact, your question is the perfect segue to my next slide. So first, Vikram, did I answer your question? Okay, great. So this is the perfect segue to my next slide, which is the question, hey, wait a second. If parametrically you can do observables before or after grooming, well, if they're parametrically similar, well, what's the ideal way of using this information? And this was actually the study of a paper that came out in December of last year by Gavin Leis and Gregory, where they studied a fascinating interplay between grooming and discrimination. So instead of thinking about discriminating jets with or without grooming, what if we discriminate jets based on a combination of groomed and ungroomed distributions? And so what they showed is that for the purposes of boosted WZ tagging, if you start off with no grooming, then they actually did a first principles calculation to give you this red discrimination curve, which shows you that, okay, you get pretty good signal to background separation. If you used groomed mass and groomed tau 2-1, then it's better in certain regions on the Rock curve and worse in other regions on the Rock curve. If you take CMS's strategy, where you used groomed mass but ungroomed tau 2-1, that gives you the green curve, which does better than both of the all no grooming or all grooming distribution. And what this paper showed through an analytic calculation is that actually the optimal way of, at least for n sub jettiness, using grooming and ungroomed information is what they called a dichroic combination. So they used groomed mass for the discrimination, but then they use a dichroic. So dichroic means di means two, chroic for color. So two different color structures that they're trying to explore using this tau 2 over tau 1 ratio. And they actually showed through an analytic calculation that if I ungroom the numerator but groom the denominator, that actually gives you the best numeric performance among all of these options. And so this gives you a little bit even more of the sense of the value of these analytic calculations for identifying optimal use of substructure information. These distinctions are ones for which the power counting can't really help me very much. Maybe the power counting could have gotten me to this dichroic, but it's not so straightforward. But if you actually do honest calculations, you can now start to explore more subtle features of jets, and in particular, this case, exploring the fascinating interplay between a combined grooming and ungroomed information for discrimination purposes. Okay, so now in my last time, I want to talk about what I think the future of these analytic calculations are. And I feel like as a field, we've come to a sufficiently sophisticated point where we can now revisit a very old question. And so I'm calling this Back to the Future, quark jets versus gluon jets, because this is an idea that traces its origin back to the very early days of QCD. But I think now with these analytic calculations, we can actually maybe start making progress to tackle this discrimination. And this is a case where parametrics doesn't help me. So this power counting method that I just described, that's insufficient for understanding quark versus gluon separation. And we just have to bite the bullet and actually do calculations to make further progress on this. So this event display that I'm showing here is actually a famous event display from JADE from 1979, showing E plus E minus to QQ bar glue. And you can just try by eye to guess of these three jets, which one's a quark, which one's an antiquark, and which one's a gluon. And the cartoon picture for quark and gluon jet formation is that quarks are associated with a color factor of 4/3. Gluons are associated with a color factor of 3. So in this soft collinear approximation, quarks emit soft gluons at a rate that's roughly half as much as gluons. So in this cartoon language, we would say that in this JADE event display, the gluon jet is the one that has the most tracks in it. And the quark and the antiquark are the ones that have fewer tracks in this event display. Now, why do people at the LHC care about quark-gluon discrimination? Quark jets are often associated with beyond the standard model signals of interest. Gluon jets are often associated with background jets of interest, or of non-interest. And but more generally, this very fundamental question of jet classification. Can I make, from a first principles perspective, a meaningful distinction between jets initiated from a quark or gluon? That's very fascinating because, of course, jets are color singlets, whereas quarks and gluons are color triplets and color octets. And yet there's still some imprint in the final state of the color structures there at short distances. And you'd like to understand theoretically whether you can make a meaningful distinction between quark-initiated and gluon-initiated jets. Now, one of the challenges for quark-gluon discrimination in practice is that if I just use this color factor information alone, the mistag rate for gluons and the efficiency for finding quarks, they are related by this color factor ratio, which is approximately 2. So quark-gluon discrimination is something that improves signal divided by background, but actually barely improves the significance of signal over the square root of background. And this is the reason why quark-gluon discrimination has not found that much adoption at the LHC, except for in circumstances where there's a high multiplicity of quark jets in the final state, such that the deviation from this color factor ratio from 2, that you can use multiple times in order to get discrimination of multi-quark signals versus multi-gluon backgrounds. Now, I should say that this idea of separating quarks versus gluon jets has a very, very long history. For example, if I go back to the late 1980s, early 1990s, there was a flurry of activities trying to do quark-gluon discrimination, where, among other things, doing things like taking the flavor and kinematics of the hadrons inside of a jet and trying to figure out whether if I bin things in terms of the transverse momenta of the hadrons, or whether they're pi plus, pi minus, pi naught, or kaons, whether I could use that for separation power. Back in the 90s, there was interest in neural network classification, using as inputs either properties of the jets like this kinematics or jet shapes. Something that's surprisingly effective is an observable that's called N90, where you take a jet and ask how many calorimeter cells do you need to account for 90% of the jet PT? And that turns out to be a good quark-gluon discriminant. So, people have thought about quark-gluon discrimination for a long time, but somehow we've revisited quark-gluon discrimination, going from black and white now to color in the LHC era. CMS, for example, has commissioned a 3-observable discriminant, quark-gluon likelihood discriminants built out of the multiplicity of hadrons inside of the jet, an observable called PTD, which basically probes how hard jets are in terms of their individual hadron fragmentation, and sigma 2, which is a measure of how elliptical the jet is. And you can see on this likelihood discriminant that this discriminant having a value of 1 is correlated with having a quark jet, and the discriminant having a value of 0 is correlated with having a gluon jet. The idea of neural networks has now gone into, again, from the black and white to the colored era, with now using techniques from image processing to use deep neural networks, or in this particular paper coming out of a Harvard group, convolutional networks, where here red, green, and blue correspond not to the colors of QCD, but to image channels of PT carried by charged particles, PT carried by neutral particles, and number of charged particles hitting a calorimeter cell. I can form images in this red, green, blue space. I can apply deep learning techniques in order to come up with discriminants that are trying to maximize the information contained in these images. And all of these discrimination strategies show remarkable performance. That is, there is performance gains using multivariate information, and you can push beyond this limit from just color factor scaling, and you can actually get pretty good background rates. So, for example, for a quark jet efficiency of 50%, you can reject now 90% of gluons. And that's using the CMS method, and you can even start pushing that to 90%. Sorry, other way. 50% quark efficiency is 90 to 95% rejection of gluons using this advanced multivariate deep network strategy. Now, this is all great. I mean, I'm all for having good discrimination power. But if you've learned anything from this talk, it's that I am someone who is a strong advocate for first principles understanding, either through power counting or through first principles calculations.
Hello.
What out of the box happens when you just take the workhorse Monte Carlo programs and ask, yes?
Could you go back? We lost you for around a minute. Could you
Around a minute.
No, that's okay. The side up, this one. Could you start from here again?
Yeah, sure. So here, using this using this CMS strategy of this 3 observable combination, you can see performance that exceeds this Casimir scaling prediction. For example, for a quark efficiency of around 50%, you get a gluon rejection of around 90%, and for and using this deep learning method for a quark efficiency of around 50%, you can even start getting gluon jet rejection factors of around 95%. And so, we're really maximizing the information inside of the jet, and there is some kind of residual information that is useful for telling us about the origins of jets as pertaining to the underlying color structure. But if you've gained anything from this talk, you can say that I am someone who's a strong advocate for first principles understanding, that I'm not satisfied with just plotting a bunch of Rock curves, that I want to understand why these observables behave the way that they do. And whereas for boosted W and Z identification, I think we can say we've done a good job, for quark-gluon discrimination, our first principles calculations are woefully behind. And one way of understanding that or seeing that is looking at the theoretical uncertainties present just in our workhorse Monte Carlo programs. So this is an Atlas study from last year, just looking at the multiplicity of charged particles coming from ordinary die-jet configurations. And there's something that's now been dubbed the Pythia-Herwig sandwich, where data is the filling, where we see the solid curve for Pythia, the dash curve for Herwig, and the data is in between. And you might say, well, I mean, that's not that bad of an agreement. If you look at the actual number of tracks that these distributions are differing by, it's differing by of order, 2 or 3 counts. So maybe that's not such a big deal. But when it comes to quark-gluon discrimination, that level of uncertainty is basically the difference between having a robust tagging strategy and having something that doesn't work at all. And so one way of quantifying this is by calculating an information theoretic quantity called classifier separation. The details of that definition don't really matter. But just if I look at this first column here, this is the classifier separation as achieved from Pythia, which is shown in black, versus Herwig, which is shown in this dashed red. And basically, this classifier separation value differs by a factor of 2. And that is a huge difference, and one that really needs to be understood theoretically to be able to say that you understand really what's happening with quark-gluon discrimination. And it's not just about this N-track observable. Actually, if you plot a bunch of different objects, variations of these energy correlation functions that I told you about before, they all show comparable levels of disagreement. And small uncertainties in the underlying distributions lead to large uncertainties in discrimination power, such large uncertainties that essentially anything that anyone says to you about being able to improve quark-gluon discrimination, that all is under this shadow of not really understanding from first principles what's really going on for quark and gluon jets. Now, I don't want to be all doom and gloom about this because there are strategies that you can use to make data-driven ways of understanding these distributions. And the field is rapidly going towards these next to leading logarithmic calculations, which are finally at an accuracy with uncertainties where you could meaningfully talk about trying to do a first principles prediction of quark-gluon separation power. And I also want to emphasize that from a new physics perspective, these quark and gluon strategies really can get you good performance gains. So I was at a recent workshop in Japan just about new physics search strategies. And here's an example of just gluino pair production where the final state has 4 quarks. And if you take the standard Atlas strategy for looking for this final state, you get this orange curve in the mass of the gluino, mass of the neutralino plane. And with the use of substructure, you go to this black curve, which has substantial performance gains, such that, if you're someone who thinks about beyond the standard model physics, you might actually want to learn about jet substructure in order to realize, quite substantial gain, where you're talking about 200, 300 GeV increase in mass reach for the gluino, which is fantastic. But if you look at the solid versus dash curves, that's the difference between a Pythia prediction versus a Herwig prediction. And that level of uncertainty is not really acceptable in this context. And so we really need first principles calculations in order to go forward. And so for me, this is where I see key tasks for the jet physics and jet substructure community. And anyone who's heard me give a talk in the past 2 years has seen these 2 plots showing that even if I just go back to the very simple case of E plus E minus collisions, that E plus E minus to quarks is well modeled and well constrained by the variety of dijet event shapes measured by LEP. Whereas in this idealized case of E plus E minus to gluons versus a Higgs boson, you can see this large spread in distributions. And this needs more input from experiments to measure these different substructure discriminants, as well as first principles calculations from theory. And unfortunately, this power counting technique that I've been telling you about does not work because CA and CF, even though they're numerically different, they're both order 1 as far as power counting is concerned. And so one just has to bite the bullet and do higher order calculations. Here we can see analytic single next to leading log calculation, including some of the effect of non-global logarithms, as well as including a non-perturbative shape function. So this dashed curve here is the best that I can do at present at predicting this distribution, which is somewhere between the Pythian and Herwig distribution, though with a fat high side tail coming from the lack of fixed order matching, probably. So that's the best that I know how to do right now. This is in some sense a call to the arms to the theory community to figure out how to predict these distributions better. You notice that I don't show uncertainties here because the uncertainties, when I only work to next to leading log, are gigantic and embarrassing. And one goal that our community should have is to push these calculations to higher order. But let's assume that we do that. Then where is the frontier? Let's say we really are able to do first principles calculations. Then where is the frontier? And in my mind, the frontier is trying to figure out whether we can use this deep learning techniques, which have exposed the fact that there's lots of information that discriminate quark jets versus gluon jets. Can that inspire us to think deeply about what information might be contained in a jet that haven't been probed thus far? And so again, assuming that we can get analytics under control, can we analytically understand information that goes well beyond standard CA versus CF color factors? And one possibility, I don't think this is a unique possibility, but one possibility about where we might go here is with these energy correlation functions. And it turns out that typical quark-gluon discriminants fall in the power counting universality class of these 2-point correlators. So energy correlation functions, angularities, certain non-perturbative moments of jets are more or less related to 2-point correlators. And as I said, 2-point correlators are constrained by CA over CF at lowest order. But if I now start looking at higher point correlators, 3-point correlators or 4-point correlators, it turns out that using power counting, you can actually understand additional color structures that can appear when you do special things. So this U1 set of observables is using 2-point correlators where I use just one angle. This U2 observable is using 3-point correlators, but I still only use one angle, and that's the key. If I go to higher point correlators, but still only am sensitive to the smallest angle between emissions, then this turns out to give us parametrically distinct behavior from ordinary quark-gluon discriminants. So if instead I had 2 angles or 3 angles or 4 angles, that turns out to be power counting extremely similar to the standard method. But if I only use one angle, then I get a new type of angular structure. And these new types of angular structures seem to be providing additional information beyond what at least I was aware of that you could use for quark-gluon discrimination. And so, again, using this EFT power counting technique, what these observables are doing is they're probing perturbative emissions. So these are all infrared and collinear safe observables. Multi-point soft gluon phase space. And in the correlations of soft objects, apparently there's extra information about the quark versus gluon nature of a jet. So you can see this in terms of this U2 distribution, nice quark-gluon discrimination. And then here's the thing that I find absolutely fascinating. This is a plot that's showing for a fixed quark efficiency what my rejection factor is. And this gray dashed line at the bottom here, that's the prediction from the CA over CF ratio. And this dashed line up here, the orange one, is the prediction from the most non-perturbative object I know, the multiplicity of hadrons inside of a jet. And what you can see is that as you adjust this angular exponent beta, you get different discrimination performance. Whereas you go to larger values of beta, actually this asymptotes to the discrimination power predicted just by this color factor ratio. Whereas you go to beta values that are small, you get additional information that pushes us up towards this multiplicity level of information. But as you go from U1 to U2 to U3, what you see is that this distribution becomes less and less sensitive to the angles and starts to really asymptote towards this multiplicity distribution. And I want to emphasize something here. This multiplicity of particles, of hadrons, that's a really non-perturbative object. Whereas these multi-point correlators, these are perturbative objects. And so it might be that we are figuring out, from a more perturbative perspective, how to count the number of emissions within a jet. And soft gluon correlations might be an avenue to explore. And it might be precisely those soft correlations which are first what's being used by these deep learning methods to gain more information. but also perhaps because they involve color correlations, an area where standard parton showers might just not be modeling that physics correctly because they only have certain aspects of correlations and not the full color structure. So this is something that I'm excited to pursue and is pushing us in the direction of really pursuing first principles calculations for a deeper understanding of the structure of non-abelian gauge theories. So now at my last slide, what I see as the future of jet substructure in 2017, I feel like we're now at the point where we can talk about not just the techniques of jet substructure, not just grooming, not just discrimination, not just arguing about ends of jettiness versus D2 or soft drop versus pruning versus trimming, but we can really start thinking systematically about jet classification from first principles. And hopefully this talk is giving you just a little bit of a flavor of the things that we can do when we dive into the analytic structure of QCD. So let me stop there, and looking forward to getting some more questions from you all. Steve.
So in the last part about gluons versus quarks, you didn't address the issue of first principle definition of the difference. What is a quark?
That's correct. Yeah. So unfortunately, for some reason, I dropped the slide that I often show about the definition of what a quark jet versus a gluon jet is. So let me talk about that in a couple of different ways. So one thing that we know about quark-gluon definitions is that jets, of course, are color singlets, whereas quarks and gluons are triplets versus octets. So that means that inevitably the definition of a quark jet versus a gluon jet is not independent of other color structures inside of the event. That is, there's soft color correlations between the jet that you're trying to study and out-of-jet radiation. And that impedes a universal definition of quark and gluon jets. Or at least that's what I thought until this paper by the Harvard group. And let me just scroll back, way back to something I didn't emphasize. So this first next to leading log plus order alpha s squared calculation, it did two things. It not only did this calculation, but it achieved it in a proton-proton collider where naively I would have said, geez, how are you ever going to predict that distribution given the fact that there's color correlations between the initial and the final state? But the realization is that actually after you perform this soft drop procedure, you drop soft correlations between final state partons. And because you've dropped those soft correlations between final state partons, it turns out that at leading power in the factorization theorem, you actually do have a perfectly well-defined notion of what a quark jet or gluon jet is in terms of a collinear Wilson line wrapped quark or gluon final state. And that is because you've gotten rid of soft radiation, a theoretically defensible in a certain limit definition of a quark or a gluon jet. And so I see that as a really great contribution to our understanding of the definition of quarks and gluons, which is that grooming not only gets rid of soft radiation, but it also gets rid of soft correlations and allows you at leading power to define what you mean by a quark or a gluon jet. Now, you might be worried, what about beyond leading power? And indeed, beyond leading power, I know of no rigorous definition of quark or gluon. The only thing that I know is that there is a definition of a phase space region which is quark enriched versus a phase space region which is gluon enriched, where what I mean by those phase space regions is in the mind of the analyzer. And so going back to something that I said early on, that thinking about jets as a method to interpret hadronic final states, one can interpret a given radiation pattern as being quark-like or gluon-like as the analyzer wishes, And then those words of quark-like and gluon-like are essentially proxies for perhaps a more simplistic notion of what quarks and gluons are, perhaps defined by just the properties at Born level. But at the level of cross-sections, we can very meaningfully talk about the cross-section for jet production where the angularity value is less than a certain number. So that is just a cross-section that we can calculate, and then we as the analyzer, we can choose whether we call that quark-like, or we can just choose it to call it the low angularity region of phase space. And then one can do those calculations both on signal and background, and one will find that definition of a cross-section will achieve some degree of signal background separation in concordance with the degree to which that signal versus background is quark-enriched versus gluon-enriched. But for me, that's the most meaningful definition of quark or gluon, is just a region of phase space with narrower or wider radiation patterns, or if you're willing to go to just leading power statements, then the definition of quark and gluon in the context of Groomed jets.
Jesse, could you go back to the slide with the SUSY bound and how that changed with jet substructure?
Yeah. There's a number of fascinating features on this plot. I'll let you ask your question in a second, but let me just emphasize something, which is that this atlas cut here, that's the standard atlas analysis. And even if you just apply substructure by itself, without using some of the standard atlas cuts, you can actually recover some of the performance that a standard atlas cut would give. And the combination of kind of standard cuts and the substructure cuts, that gives you this ultimate performance gain. But that wasn't your question. So what's your question?
So my question is, what's the uncertainty on the quark-gluon fraction of the background? And presumably the background to this is something like Z plus jet with some ISR?
Good. So you're pointing out a very important point, which is that there are two types of uncertainties that we're talking about that are kind of mixed up together in this Pythia versus Herwig comparison. So one uncertainty is the one that I was referring to, which is that to the extent that you can define a quark versus gluon enriched region of phase space, we don't know what quark and gluon enrichment really means in terms of the jet shape observables. But you're pointing out an equally important part of the problem, which is that if you don't have fixed order calculations of the background that tells you about the wide angle relative production rate of quarks and gluons in the background, that is an additional source of uncertainty. And what I don't remember about this paper is whether they actually solved this by making sure that they used the same underlying production mechanism. That is, I forget whether they actually did this calculation where the hard scattering was done with MadGraph interfaced with Pythia and Herwig only for the showering. My memory is that they did do that, but I don't remember off the top of my head. And that mitigates part of your concern about that source of uncertainty. But you're absolutely right that there is a source of uncertainty associated with the background composition, and that is yet another thing that has to be accounted for. That's more of the fixed order world. I'm talking about the more resummed jet shape world where there's equally perplexing uncertainties.
I'm also just worried about the difference between Herwig and Pythia, and that difference not being as important as the fixed order calculation.
Right. So again, here, well, assuming that this is actually hard scattering with MadGraph, then your concern is been addressed. Or at least I think it's been addressed. Let me ask you: does that address your concern? If it's really hard scattering was done with the same program, namely a fixed order generator, then would you be okay?
No. Well, the issue is the uncertainty in the fixed order, right? Is that going to be more important for your uncertainty on this bound versus the difference between Herwig and Pythia? So, like, are you just incrementally gaining with jet substructure but not really solving the larger uncertainty?
Good. Okay. So there are Right. So what I would say is I would say that your uncertainty that you're worried about is already a concern that we should address at the level of the Atlas style cuts, which are cuts which make sense at fixed order. And yes, there are uncertainty bands there. And substructure, I think, just grows those uncertainty bands. I'm not aware of a way that it would shrink it unless there was some clever way of actually using the substructure to maybe better validate the background composition. So, for example, if your background is composed of background that is 4 gluon-like, 3 gluon-like, 2 gluon-like, and 1 gluon-like, I guess you can, in principle, establish multiple validation regions where you try to separately match those validation regions to the data. So maybe that's something that one can pursue. But I think that the uncertainty you're talking about is already present at the level of the Atlas cut, and I'm not aware that substructure would really go to improve that.
One more question, Jesse.
Great.
Can you go to slide 55, Jesse?
Slide 55, yes.
Yeah. I just wanted to ask, I mean, you were making a point how the classifiers are very different, values are very different for Pythia, Harwig, etc. But I also noticed that there is a really large dependency on the angularity and the angle and the beta, right? These kappa choices of kappa and beta, which are going somewhere in the analysis. So would you like to comment on that? Because I noticed that the ordering of the classifiers for different Pythia, Harwig, etc. seems to remain very similar, but the spread is quite different for different choices. So is it that
Good.
robust? I mean, I just want to
Good. Okay. So these observables here have been chosen. So let me just narrate to you what they are. So this first column, 0, 0, that's multiplicity. 2, 0 is PTD. 1, 0.5 is known as the Lesouche angularity, because Lesouche is where we decided to give it a name. 1, 1 is the jet width, and 1, 2 is the jet mass. And as you can see, there's different discrimination power between these different observables because these are all probing jets beyond the color scaling in an interesting way. And what you can see is that, for example, among these three angularities, Lesouche angularity with 0.5, width with 1, and mass with 2, that the one with the smaller exponent is the one that does better. And that can be semi-understood from a theoretical perspective because the differences between quark and gluon jets is enhanced when you focus on small angles. And this particular one that I'm highlighting here is sensitive to the smallest angles. Now, before I started looking into this, I was not surprised by this first column or the second column because those are infrared and collinear unsafe observables. So I would have said, look, the hadronization model would dramatically change those observables anyway, so why should I trust them? The surprise is that these three that I'm highlighting are infrared and collinear safe observables. So I would have thought that those would be ones that would be well modeled by parton showers, and they're not. Now, the point that you make is quite fascinating, which is that the ordering of the different discriminants is kind of similar between the various programs. And in fact, it goes a little bit deeper than that. This Harvard study that I told you about with deep learning, they showed that if you trained a deep network on Pythia and applied it to Harwig data, or vice versa, you trained a network on Harwig but then applied it to Pythia data, that what you would find is, of course, whether you use Pythia or Harwig, the discrimination power changed. But the discriminant as found by the networks in both cases were basically the same, such that a network trained on Harwig did equally well on Pythia as a network trained already on Pythia. And so this somehow points to the fact that these programs are getting something right about the relative order of certain features within the jets, and that all that's happening is that the overall magnitude of the separation is changing. And I have a couple of theories about why that might be true. One of the simplest theories about why that might be true is that a primary difference between these Monte Carlo programs is simply the default value used for alpha S. And if you take all quark-gluon discriminants, they all depend on the value of alpha S. And they basically all depend in a monotonic way on the value of alpha S, such that as you go to bigger values of alpha S, the discrimination value improves. So at the end of the day, we may just learn that the primary difference between these Monte Carlo programs is just the default value of alpha S used in the final state shower. And the reason why the discriminants are overlapping is just because, discrimination is in the same order, is simply because of using different alpha S defaults. And that may indeed, at the end of the day, be the reason that explains this behavior. And then it becomes a more puzzling question: why are these programs using different values of alpha S, given that they've all been tuned to data? And that's something that we've also started to explore a little bit. But it's very suggestive, the thing that you pointed out, and it's something that gives me hope that we'll be able to understand ultimately what these differences are.
I ran through your slides, but I didn't see what your N3 was, which you said that is for the people who are interested in tops might ask me about N3, but I didn't see anywhere on the slides.
Yes, and so somehow my backup, I must have deleted or just forgot to include all my backup slides. I think oh, that's right, sorry. I copied and pasted this from a collection of other talks, and so I just forgot to include the backups. So, so I can tell you the definition of N3, and because I have the picture back here. So here on slide 41, you can see this three-prong top jet, and what's being calculated is 2E4. And if you want a nice exercise for yourself, you can say, okay, given that the numerator is 2E4, what is the denominator that you need to use in order to have something that is boost invariant? And so it's 2E4 divided by, 1E3 squared. That's the N3 observable.
Okay.
And has a parametric behavior similar to N sub jettiness. And it's an observable that actually is, that's an observable that's actually challenging our ability to use the power counting technique. Top quarks have more scales inside of them, or more accurately, the backgrounds to top jets have more scales inside of them. And so the power counting technique is a little bit more delicate in that case. But if you test this N3 observable, you find that it has very comparable performance to N sub jettiness when applied to groomed jets. And then for ungroomed, it doesn't actually work all that well. But it is still something that's worth potentially exploring.
Thank you. Actually, can I ask yet another question? I'm asking questions. I'm not making comments. Okay. Now, say for the top quark, for example, if you have a lepton, which also quite often, if it's a tau and it would look like a jet, for example, have people thought about it? So you will have two jets, one tau jet and one quark jet, B jet, and missing energy. So
yeah,
I am not very familiar, so I wanted to know how people handle top taggers in this situation. Oh, no, it's a semi-leptonic. Tau. Tau itself will also make a jet.
Yeah.
So I wanted to know whether...
Right. So I would say that most of the jet substructure literature has been focused on the all hadronic channels, but it's becoming quite clear that if I'm trying to do systematic jet classification, I shouldn't just rely on just the 70%. Of course, there's leptonic decays. And so there are strategies for boosted tops in
Hello? Hello?
I'm not aware of anything, but maybe someone in the audience is aware of what you can do when you have a semi-leptonic top where the lepton is actually a tau. But you know, I used to say, look, all the fun stuff for jet substructure is clearly in the all hadronic channels. But now, having played around with this enough, now actually figuring out how to maximize your use of all available information. And so for semi-leptonic channels, that's something where I think more can be done, especially in the top case, and also in the Higgs case, where we talk about Higgs to BB bar, but there's additional information in principle trying to look at Higgs to ZZ star or WW star, where you have a combination of hadronic and leptonic final states. And if we really want to squeeze out information, we could do that. And then if you really want to go to like really systematic classification, and you're not content at only looking at the objects that are shown here as being highlighted, and you really want to start looking at even neutrinos and electrons and muons, then all you have to do is go to a 100 TeV collider, and at 100 TeV, leptons start to have sufficient amounts of U and Z radiation, which can decay hadronically, that you can now even start talking about neutrino jets and electron and muon jets if you'd like. And that, again, goes in the direction of really trying to extract as much possible information about hadronic final states as you can.
It must be close to midnight now.
It is 11:30 here. I've had a lot of fun, and hopefully this was useful. I am very sad to not be there in India with you all, but wish you a successful rest of the workshop. And if you have further questions, feel free to send me an email, and be happy to respond.